Welcome to Physics Made Simple. Today's lesson is Measurements Made Simple by Dr. Eid. Physics is quantitative. Just like most of sciences, we try to measure and we try to be as accurate as possible and as precise as possible. And that is because in science, we do a lot of experiments and we are always aiming to get as close as possible to the true value that we end up getting so that whatever experiments we're working on is actually repeatable. In all of sciences, we use what we call the SI system or the international system. And in this system, we have to make sure that we use the same units all across the board so that whoever is repeating our experiments is able to come up with the same numbers and not off. For example, when we are measuring temperature, we use Kelvin. Here in the United States, you always hear um, Fahrenheit, and in other countries you always hear Celsius. But in measurements in science, we always try to convert that to Kelvin, and we'll talk about that. Mass, or the mass is different than weight, and you have to remember that. Mass, we always use the unit grams. Here in the United States, we use pounds. And when in science, we do not use pounds, we use grams. For the length, we use meters, and for current, we use amps. And we'll talk more about that when we go over electric currents, and same with temperature. When we measure any temperatures, we'll talk how we can convert from the Fahrenheit or Celsius to Kelvin. Again, more units. When we are measuring time, we remember that we are always using the unit seconds. When we are measuring the amount of substance, and this is more chemistry, but we will also need it or need to refer to it in physics. It is moles, and when we're measuring volume, it is in milliliters. Now, one of the things I want to focus a little bit more on is density. Density is a measure of how much mass is contained in a given volume. Let's say we have a small marble. Okay, how much matter is inside that marble is going to be completely different than, for example, a ball, a, a ping pong ball, because a ping pong ball um, is empty on the inside, or the matter inside it is a lot less than the matter inside the marble. Even though the marble looks smaller, when we go ahead and measure the mass of either one of them, we're going to find a big difference because of the amount of matter inside each one of them. So to calculate the density of something, we have to be able to figure out the mass, and we have to be able to figure out the volume. And we're going to go over that in a minute as well. So in science, as well as physics, we have to use specific tools in order for us to reach an accurate and precise results. And these tools uh, are very well known within the scientific community. For example, in chemistry, we use a lot of test tubes, graduated cylinders, um, and beakers in order for us to measure volumes of substances. To measure the time, for example, we use photo gates, and these are a lot of fun when we work with speed, and we'll talk about those. We use stopwatches. We use we call them God clocks in some places. For example, in the hospitals, because everyone in the hospital must be using the one clock for the whole building. To measure lengths, we can use measuring tape, rulers, and calipers. And of course, the unit for length is meters, and we're going to talk about that in just a minute, which is the metric conversions, or the conversions from one unit into the other. Temperature, again, we use Kelvin and we use thermometers. And when we're talking about mass, we are always using grams as units, and scales are the commonly used measuring tool. So metric conversions are very essential in every science, including physics. And that is because sometimes we make a measurement and it is in one unit, but the question is asking for it in another unit. Now that unit could be a larger unit or it could be a smaller unit. So sometimes we have to convert from a smaller unit to larger unit, which means we have to move the decimal in one direction. And sometimes we have to go to a smaller unit. We have to move the decimal in another. So in other words, if I have a meter and I need to see how many milliliters I have in a meter, I have to multiply. Okay, so millimeters are in the thousands values. So if we look at the table, milli is in the thousands. So if I have 1 meter, every 1 meter on a meter stick, if we are there to count every tick on that meter stick, it's going to be 1,000 of those. It's 1,000 of those millimeters. And then if we are going to be counting every centimeter is actually, every 1 centi is 10 milli, but it's every 1 meter is 100 of centimeters, and it is 10 decimeters. Now let's say we need to compare that meter stick to kilometer. Well, that's a part of a huge. So how many parts of it? It is 1 of the 1,000 meter, part of the 1,000. So which means we need to divide by 10 every single time we go backwards. So if I have 1 meter, how much or how you can convert from that meter to kilometers? You are moving that decimal backwards by 10. So 1 meter is a 0.1 of decameter. It is 0.01 of a hectometer, and it is 0.001 of kilometer, because it is part, that 1 meter is part of that huge 1,000. So we divide if we are going backwards, if we are going from small to large, and if we are going from large to small, we multiply. So we'll go ahead and have an example on the next slide. So this is one of the conversion charts that I used to use in my classes in order to help students. And those arrows, sometimes they stick into their heads. So that if the basic unit is gram, for example, and I want that to be converted to kilogram, part of a kilogram. So how many kilograms are in 10 grams of sugar? How can you convert the 10 grams into the kilograms? So it is part of a huge, the kilo is 1,000 grams. The 10 grams is much smaller. So to go from that, I am moving that decimal 1, 2, and 3. Let's say how many milliliters are in 20 liters. Oh, 20 liters, that's a lot of milliliters, a lot of small parts. And it is 1, 2, 3 steps. So I am moving that decimal forward 3 times. I am multiplying by 10, and then by 10, and then by 10, which is by 1,000. And the same thing if you're going backwards. Let's say how many milliliters, how many liters are in 10 milliliters. So I am moving from the milli all the way to the liter. So that's part of a whole or part of a large. So I am going backwards, therefore I'm going to be dividing, therefore I am going to be moving uh, my, uh, my decimal backwards. Another tool that we use in, I've mentioned earlier, in physics and in all other sciences is basically the triple beam balance. Um, this is usually what you basically use in your school lab. You can measure the mass of a regular object or the mass of an irregular object, and it's much easier to go ahead and use the balance for an irregular object. It's since if it's a an object that's measurable due to its normal shape, we can go ahead and use the normal formulas. So the mass of an irregular object was easy to explain and easy to go over in the previous slide. Now, how can I find out the volume of an irregular object? To do that, we use the water displacement method. And as we can see here, we are using the graduated cylinder because it gives us more accurate results for the amount of liquid. We start off with a certain amount of water liquid that we fill up or pre-fill the graduated cylinder. In this case, it's 64. And then we add the irregular object, whatever it is, to that graduated cylinder. And we notice that the actual volume on the graduated cylinder has moved. In order for us to find the volume of this irregular object, we subtract the final volume or the final reading on the graduated cylinder minus the initial reading of the graduated cylinder, and that will give us the volume of this irregular solid. In this case, it's a ring, but I mean, it could be any object that is irregularly shaped. So now we're able to find the mass of the irregular object. We just learned how to find the volume of an irregular object. Now we are able to find the density of that object because density is equal to mass over volume. The story of the water displacement is very funny, and it may help you remember um, uh, this process. And Archimedes was very frustrated. He's a scientist, frustrated to figure out how do I find out the volume of an irregular object. Okay, I can find the mass using a balance, but I still cannot figure it out. So after pretty much giving up, he decided he wanted to take a cold bath. So he went ahead and turned on the water with his tub, and he totally forgot about it because he went back to the lab and he was trying some more and more and more methods. And then he came back and it was already overfilled. Turned off the water, and then he got into the tub. As he got into the tub, there was a certain amount of water that actually overflew, like the outside of the tub. And this is when he realized, he was like, "Oh my gosh, Eureka!" And he was so excited that he ran out of the house screaming in the city, "Eureka, Eureka!" Which is I found it, I found it. Which is he found how to calculate the volume of an irregular object that we just explained. Hopefully this will help you remember um, uh, the process. Okay, so a quick recap on the measurements. We can measure temperature by using a thermometer, and which is the amount of heat energy in an object or a substance. In order for us to measure time, which is the duration of an event, we can go ahead and use a clock or a watch, or we call it stopwatch in science, or we can use photo gates. In order for us to measure the length of a substance, which is the distance from one point to another point on an object, we can use measuring tape, we can use um, the meter stick, and so forth and so on. The volume of a regular solid, we can measure length, width, height, length times width times height, and this is the normal formula that we use in math. Significant figures are basically just like they sound. The, the numbers or the digits that are very significant in any number provided. Uh, we have to remember, in order for us to keep accuracy and precision, we have to always remember that all non-zero digits are considered significant. All zeros that are between non-zero digits are significant. Now, you have trailing zeros on the right side and trailing and leading zeros on the left side. These will be changed when we use scientific notation, and we will learn about that in just a minute. So numbers that are leading or to the left side of that number, these we will be able, we do not consider them significant, therefore they can fall by multiplying by 10 to the power of, and because we are moving them backwards, it's going to be a negative number. And the ones that are trailing or at the end, these are going to be in the positive side, or times 10 to the power of a positive number. So if we move them, so we'll go ahead and take a look at some examples. So as I said, scientific notation is a method that was developed by a scientist to go ahead and make the numbers easier to read. Again, significant figures, we said the whole digits, the non-zero digits, we cannot change, but we can go ahead and move the decimal forwards and backwards as we multiply by 10 to the power of. So that being said, first we place a decimal point after the very first digit and very first digit only. Then we multiply by 10 and write the power based on the number of places the decimal had to move to drop all the zeros. That being said, let's go ahead and take a look at that very first number. So the decimal notation is 3.4560000000000. So we can go ahead and count how many. That decimal, if it needs to move all the way to the right, it needs to move 12 times. In order for me to write a scientific notation and go ahead and drop all these zeros, again, we do not touch the whole numbers, okay? And we move the decimal to only one spot, which is the first digit, and then we multiply times 10 to the power of how many times that that decimal had to move to the end. So 3.456 times 10 to the power of 12, because it's a large number, okay? So we made it smaller by saying it's 3.56, but that number has this many zeros. So that decimal had to move 12 spots in order for it to give you the full number without having to write it in the scientific notation. So that being said, let's go ahead and take a look at another number, but in this case we're moving backwards, which is a very, very, very small number. So when we're working with very small particles, we are going to have a lot of zeros. So I have, instead of having a gram of a substance, I have a lot less. So I have a milligram, or even smaller than that, which you will see in chemistry. You will have a number of moles, and then we'll convert it to grams and whatnot. So I have this number, which is 0.00000000725. Okay, well, again, I'm going to move that decimal to after the very first digit, which is, I'm going to move it backwards. 1, 2, 3, 4, 5, 6, 7, 8 times. but I moved it back in the opposite direction. It's a very small number, but I'm identifying it in a large number. Therefore, it is going to be negative. So I moved it in the opposite direction. It's going to be minus 8. So 7.25 times 10 to the negative 8. Let's go ahead and go over it one more time. If you are moving the decimal backwards, it's a positive power. If you are moving the decimal forwards, it's a negative power. So what I want to say again, if I am making a small number, a very, very, very small number, look bigger or look nicer, I am going to make it look more scientific by moving the decimal in front of one digit, in front of the first digit, and then all these zeros to the left side are going to be negative. If I am moving the decimal forward, it's a huge number, but I don't want to write this huge number, then I'm going to move the decimal, which we assume at the end, after the very last zero, there's a decimal. I'm going to move it backwards however many spots. And in this case, it was 12, and it's going to be a positive number. Finally, let's go ahead and practice. I am going to wrap up this lesson with hopefully a way for you to practice the measurement lesson step by step. So first, we talked about how we can find out the volume and the mass of an irregular object using the tools that we normally use. We went over all the tools. So right here, the first question is asking us, so what tool would you use to measure the volume of a rebar? Of course, we talked about it. We said a rebar is an irregular object. We don't know how to measure it just by shape. We'll go ahead, because it does have ridges and whatnot. Let's go ahead and use the water displacement method. And to do that, we'll go ahead and do what? Measure a certain amount of liquid, place it in a graduated cylinder, and write that down. The initial volume is 13.5 milliliters. The next step for us to do is to go ahead and add that rebar into the graduated cylinder. We add the rebar into the graduated cylinder, and we note the difference in volume between the initial volume and the final volume. So the final volume is 22.4 milliliters. Initial volume is 13.5 milliliters. What do we do to find out the volume? We go ahead and subtract. 22.4 minus 13.5 is 8.9 milliliters, and now we have the volume. Our second question is asking us to describe the process and calculate the volume. We did. The third question is asking us now to find the mass. So, mass of a rebar, very easy. We know that we have a tool. The tool is a scale. We go ahead and add the rebar to the scale, and we end up with a mass. The mass is 69.658 grams. Awesome. So, can we determine that number in significant figures? Sure. I can go ahead and count how many significant figures we have. It looks like all of these are significant. 69.658 are all whole numbers, all whole digits. Guess what? They all are important and significant, and we will not touch them. Now, let's look at that very last question. The speed of light in vacuum, where there's no air, vacuum is no air, is, look at that, 300 million meters per second. Okay, how can I write that value using scientific notation? Okay, I am going to look at the significant numbers. There's 3.0. Okay, 3 times 10. I am moving that decimal back because it's 300 million.0. Therefore, I am moving that decimal backwards. 1, 2, 3, 4, 5, 6, 7, 8. So it's 3 times 10 to the 8 meters per second. Thank you, and I hope that you enjoyed this lesson. If you have any questions, please make sure you write that in the comments or email me. This is Dr. Eid. Please subscribe and like.